In this video, we're looking at first-order linear systems, and we want to drill down specifically to those with constant coefficients and that are homogeneous. So here's an example. dx dt equals x minus y, dy dt equals negative 2y. So this is linear because we just have an x term and a y term, actually a 0x term and a y term here. That's what makes it linear. It's constant coefficients because we just have the coefficients for the x's and the y's are just 1, -1, 0, and -2. No dependence on time on the independent variable. They're constants. And finally, it's homogeneous because we don't also have a term that doesn't have x or y on either of these. We don't have, plus 3 or, minus 4t squared or anything like that. That's all zeroed out. So that's what makes it homogeneous. And so this is an example of that. We learned that we can also write this in matrix form as follows. So the coefficients go into a single square matrix, in this case 2 by 2. Right? And if you check regular matrix multiplication, this row times this column, you'll get this. And this row times this column will give you this. And so we could write this, we could use a capital Y with an arrow on top because it's a kind of a vector. It's two components, equals a y. Right? And in this formulation, the fact that it's constant coefficients is the fact that a is just constants. And it's homogeneous in the fact that we don't have a plus b term. We don't have that. Okay, so what we already know is that if we were given initial conditions, of course we could apply Euler's method and solve it numerically. We also know that with some technology like our calculators, we can generate a direction field, and that's a more general thing that doesn't require initial conditions, and we can see in the phase plane which way solutions would go in terms of x and y changing over time. So that's a qualitative approach to the solution. So both of these are at our disposal. But we want to be a little bit more specific and start working our way toward perhaps an analytical solution, in other words, a formula solution. And we're going to be guided by the fact that this is linear, and we're going to be able to use a technique that we used before when we had a single linear differential equation. So let me talk through that now. Okay, so I've just rewritten the same system, and let's give ourselves some initial conditions that we want to solve for. Let's say x of 0 equals 3, y of 0 equals 5. In terms of the matrix formulation of things, we would just say y of 0, the vector capital Y of 0, it starts at the vector 3, 5. Right? Again, the top component is your x, your bottom component is your y. So two single initial conditions or one vector initial condition, either way. Okay. Now, I'm going to write down the following vector, e to the t and 0. And I'm going to claim that this is a solution to the differential equations, but not our particular initial condition. Well, you can see it's not the solution to the initial condition. When you plug in 0, you would get 1, 0. In fact, let me write that down. y1 of 0 is 1, 0, not 3 and 5. Okay, but it does satisfy the differential equations. So let's check this out. So if I look at dx dt, it's supposed to equal, so question mark equals, x minus y, right? That's our initial condition up here. Well, in my solution, this is my x, and this is my y. This is what I'm claiming is a solution. And the derivative of dx dt is, of course, e to the t. and x minus y would be e to the t minus 0. So that definitely checks out. On the dy dt side of things, dy dt, does that equal? Well, it's supposed to equal negative 2y. Well, y is 0, so the derivative of that with respect to t is 0. And negative 2 times 0 is 0. So that checks out as well. So sure enough, it satisfies both differential equations. It is a solution to the system, but not matching our particular initial conditions. Okay. Now I'm not saying where I got this solution yet. Let me just say that up front. I'm just proposing that. That was a proposed solution and it did work out. We'll have more to say about where that comes from in the future. But I need to establish some guidelines and some principles first. Okay, so I'm going to do it again. I'm going to give you another one. Y2, and it's going to be 1/3 e to the negative 2t for x and e to the negative 2t for y. But I'm choosing to write these in the matrix form. I don't have to. I could have written x equals boom, y equals boom in both of these cases without putting brackets around them. Either way, the matrix notation is just an alternate notation that we can use. And again, I'm going to claim that this solution is a solution to the differential equations, but it doesn't satisfy the initial conditions. Let's just see, y2 of 0, right? If I put 0 in, I can see that I get 1/3 and 1. So definitely not 3 and 5. Okay, but I can check that it satisfies the differential equations. Dx dt. So remember, this is my x, 1/3 e to the minus 2t. So that's negative 2/3 e to the negative 2t. And that's supposed to equal x minus y according to the dE. And if I do that, 1/3 e to the minus 2t minus e to the minus 2t, yeah, 1/3 minus 1 is negative 2/3, so that checks out. Dy dt, does that equal negative 2y? Okay, so yeah, you can kind of see that it works. The derivative of y is going to be negative 2 e to the minus 2t, and that is negative 2 times y, negative 2 e to the minus 2t. Check. So I've got these two solutions. Again, they don't get me my initial condition, but they both work in terms of the differential equations. Okay, so the point of what I'm doing here is the following. If you can get two different solutions to your system, then you can use those two to get any other solution. In other words, we essentially have a general solution. Let me explain. I'm going to claim that the general solution will be arbitrary constant times y1 plus arbitrary constant times y2. So y1 and y2 we already know are solutions, and I'm going to claim that if you sort of combine them in this way, this is, to use linear algebra terminology, a linear combination of those two solutions, I claim that that will also be a solution. And then I'll further claim that I can pick my C1 and my C2 however I want, and I can pick them to match whatever initial condition I have. So let me try to do that. Let me try to get pick a C1 and a C2 to give me my initial condition of 3 and 5. So first of all, let me write down what this looks like just as functions. My y, let me do it this way. All right, x of t, y of t, claiming that this is C1, and then my y1, remember my first solution was e to the t and 0, plus C2, and it was 1/3 e to the negative 2t and e to the negative 2t. Let me just real quick write it also in non-matrix notation. I could just simply write x of t equals c1 e to the t plus, and I guess it would be 1/3 c2 e to the minus 2t. And y of t would be, well, c1 times 0. And then I'll have c2 e to the minus 2t. Right? So I can write it either this way or this way. And I'm claiming that this is the general solution to my system. C1 and C2 can be found to get 3 and 5. So let me show you that. So I want the answer to be 3 and 5. And that'll be C1 times, and again, when I plug in 0, right, I get 1, 0 here. And I get 1/3 and 1 here. Okay. Now this is just a system of algebraic equations, and they are linear too. So as we've seen, several times in this course, you can solve it in a high school way, substitute, etc. You can do RREF, however you want to do it. This one is pretty easy because we already, right from the start, know that C2 equals 5, and then I can just sub that in here. And so I get 3 equals C1 plus 1/3 times 5. I get C1 equals 4/3, I believe. Okay. So C2 is 5, C1 is 4/3. And so my final solution, my specific solution, is that y equals 4/3 of that y1 plus 5 of the y2. Or, to break it out a little bit more, x of t, y of t equals 4/3 e to the t 0 plus 5 1/3 e to the minus 2t e to the minus 2t. Right? Or there was a little bit of a problem of there's a million ways to write these things. I can just put this all together, right? I could do 4/3 e to the t plus 5/3 e to the minus 2t. And then for the y of t, I would just have 5 e to the minus 2t. And there we go. And then finally, I can rewrite that like that without any matrix brackets at all. Just two separate formulas, right? Those two together constitute a solution. So, any of these three are sufficient. There's 3 different ways to write it. Okay, and you can check for yourself, which I haven't done yet. You can check for yourself that any of these solutions, which are all equivalent, they do satisfy the initial condition, and they satisfy the original differential equation. Okay, and in fact, let me just show that this always works. Call it the linearity principle for homogeneous linear systems. If y1 and y2 are solutions, then so is a linear combination of them. The reason this works is, and this is best shown using the matrix notation, if we have our linear homogeneous differential equation system, dy dt equals a y, right? And if we know that y1 and y2 work, so we know that dy1 dt does equal a y1, and dy2 dt does equal a y2. Okay. Then we can check, we can verify that when we put this linear combination in, so if we do dy dt, so that's the derivative of c1 y1 plus c2 y2 right? Well, we know derivatives, right? We know like from Calc 1, right, that derivatives, the derivative of two things added together, the derivative can go on each one. And we also know that the constant multiple rule, that constant multiples come out of the derivative as well, right? So in the end, it's just C1 times the derivative of Y1 plus C2 times the derivative of Y2, right? So hopefully that made sense. And now we know, again, what dy1 dt is ay1. And dy2 dt is ay2. Okay. And now we're dealing with matrix multiplication, which also kind of distributes in the normal way. In other words, I can factor a out. And that leaves c1y1 plus c2y2, which was my original y, the original thing I substituted in for y. So I get a y. And so sure enough, read from left all the way to the right, dy dt does equal ay, which means it is a solution. So that proves that this linearity principle is always going to hold. And so it's, if you can find two solutions to the homogeneous system, then you form a linear combination with arbitrary constants, and that's your general solution. This generalizes our old first linearity principle for single DEs, which said that if you had dy dt equals ay, so that's a linear constant coefficient homogeneous differential equation, and we don't even need constant coefficient for this linearity principle, but it's homogeneous because we don't have plus b. And if we found any solution to it, y1, then c times y1 was also a solution, right? That was our first linearity principle, that if you found any solution, then just multiplying by c would also work. So there's only one here. Now we have two. And the way you combine two is the linear combination. C's in front of each of them, and you add them. All right. I should also say that if you had three differential equations, three quantities, right? So again, linear, homogeneous. Then what you would want to do, I mean, what I said was true, that a linear combination of any two will work, but actually what you would want here are three. You would want C1, Y1 plus C2, Y2 plus C3, Y3. You would want three of them. So here's sort of one, here's three, but the example I've been showing you is two. So it works with sort of any size problem, is my point here. Okay. One final note on this is I've been cavalierly saying that when you create this linear combination, you will get the general solution. Well, it will be a solution, but it won't be a general solution unless those two solutions that you found, y1 and y2, are linearly independent. If they're not linearly independent, then you won't have a sort of enough freedom, you won't have enough degrees of freedom with your C1 and C2 to get any initial conditions covered, if that makes sense. So you need linear independence to guarantee that this thing right here will be solvable for any initial conditions. And yeah, you need linear independence. Now when you're talking about two, so when we're talking about a system of two differential equations and we're talking about two solutions, it's easier. Linearly independent just means not multiples of each other. Right, because in that last problem, for example, instead of doing y1 equaled e to the t 0 and y2 equaling 1/3 e to the minus 2t e to the minus 2t, what if instead I had just gone with y2 equals 7e to the t, and 0. That is a solution, just like e to the t 0 is, right? But if I combine those two, I won't have enough freedom to get any initial conditions that come my way. And in fact, this one's very easy to see because you see I'll always have 0 in the y component, in the second component. I'll never be able to get anything else in the second component. So this would be not general. And of course it's because this y2 is just 7 times the first y2. Or likewise, if I kept the original y2 but changed my y1 to just be like 5 times that guy, well, that's not going to be enough, because when you do a linear combination of two things that are multiples of each other, you're just getting another multiple of it. So it's not enough. You need two like truly different solutions, in other words, linearly independent. Being not multiples of each other is enough for 2. If you had 3, if you're doing a system of 3 differential equations, then it's a little bit trickier to determine whether or not the 3 solutions are linearly independent. You need a little bit of linear algebra. You have to be reminded of some of the techniques from there. We won't get into that right now. Okay, so that's the basic idea. Now what I have not done, again, is shown you where the 2 original solutions came from. But at least now we know that if we get those solutions, we can combine them to get a general solution.